Hello everyone, nice to talk to you all. So let's continue our topics on the fundamentals of environmental engineering and science. So this class we're going to talk about the meteorology and air pollutant transport. So before we introduce the new contents, let's again do a recap of our last class. So last class we introduced the other two types of criteria air pollutants, right? So sulfur dioxide and nitrogen dioxide. So we introduced how they're being formed. Also, we introduced their removal methods. So more specifically, sulfur dioxide can be removed by a pre-combustion and post-combustion method. So pre-combustion method involves the Claus process, which basically converts the sulfur dioxide into solid sulfur, and we can make a big profit from it. And in terms of the post-combustion, we'll use the scrubber to remove the sulfur dioxide, and that's typically used in coal-fired power plants. And in terms of nitrogen dioxide, we introduced a method which is happening in combustion. And we introduced that actually the higher temperature, the higher the residence time, and also the higher the oxygen content will lead to more nitrogen dioxide formation. That's why we will modify the combustion method. We introduced a method that's called the overfire combustion. So basically, overfire air during the coal-fired combustion, and that can control the NOx formation. Okay, so in this class we're going to introduce the meteorology. So we introduced quite a lot on the air pollutants, but actually, although these methods can, those control methods can remove most of the air pollutants, there are still an enormous amount of air pollutants being generated from different types of industry or coal-fired power plants. Right? And under this situation, the meteorology will play a quite important role because it is the wind that is actually carrying a lot of these air pollutants. And if unfortunately you're living downwind of an air pollutant or downwind of a coal-fired power plant or downwind of an industrial plant, then sometimes your life might be affected by these air pollutant transport events, right? So specifically for the pollutant transport, we're going to talk about three aspects. The first aspect is about the wind, right? The wind patterns. The second aspect is about the atmospheric dispersion. So this dispersion involves the stability of our atmosphere. And the third aspect is more on the design of the stacks, which can mitigate these pollutant transport. Okay, so let's talk about the first aspect. So we know that these air pollutants can be transported by winds. So what is causing the wind? We know that, for example, if at A location and at B location, there's a wind happening from A to B, we know that the force that's driving the air to move around is actually because of the pressure. So if the location A has a higher pressure, then and B has lower pressure, then this will cause the air to move from A to B, right? And further, what is causing this pressure? So the pressure is related to the temperature at each location. So for example, if the B location has a higher temperature, then what that means is that the air will rise up, right? The warmer the air, the higher it rises. If A has a lower temperature, then the air will settle down. So by having this air motion, basically we create a vacancy or vacant spot of the air, and this is helping the air to be transported from A to B location. And actually, this kind of air movement is happening both in the regional scale and in global scale, and that's why we have to consider the transport of these air pollutants. So first, on the regional scale, so here what I'm describing is a process that's called the land-lake breeze. So people also call it as land-sea breeze. Okay, so basically it involves the wind formation between land and water. So why are we having this type of movement? So we know that the land and the water will have different heat capacities, right? So what this simply means is that during the daytime, let's say if we look at the second picture here, so during the daytime, then we know that the land will warm up faster, right? So basically the land will have a higher temperature, while the water, since it has a much higher heat capacity, so the temperature rise will be smaller. So let's say it just rise a little bit, right? So this will involve a difference in the air density. So basically the warmer location over the land the air will rise higher up, right? Well, over the lake or over the water, because of the lower density, the air will settle down, and this will cause the wind to be blown from the water over the land, and this is caused by the temperature difference and also caused by the pressure difference, and we're forming this cycle here, right? So this is during the daytime. So what about during the nighttime? So if it's during the nighttime, then we know that because a lot of heat was stored during the daytime, right, in the water, so the temperature decrease over the water will be lower, while over the land, the temperature will decrease quite a lot. So this will let the air to settle down faster over the land, while the air can rise up over the water because of the higher temperature, and this is going to form this cycle again, right? So now let's think about the situation. For example, we're setting up a coal-fired power plant at this boundary here. We know that coal-fired power plant, it's typically set up over the water. It is mainly because the heating of basically the combustion generates a lot of heat, right? This heat have to be exchanged with water or with the boilers inside the boilers. So that's why we have to extract water from the water sources and then also dump a lot of water into these water body, right? So that's why the coal-fired power plants are typically set up near the water systems. So because of that, let's look at how the pollutant are going to be transported, right? So what this means is that during the night, the pollutant will be transported towards the water, which is causing less hazard. But during the daytime, the pollutant will be transported inland, right, inward. So then that might cause some issues if there are people living nearby the coal-fired power plants. Okay, but you can see that this air motion or this pattern here just happens every day, right? So this is also the regional pattern, which is alternating actually every day. So similarly, there is another type of breeze, which is called the mountain valley breeze. This is very similar to the land lake breeze. So what happens in a mountain valley breeze is, let's say if we draw a mountain here, and then this is the valley. Let's say there are some trees, some buildings, right? So what happens here is that typically we know during the daytime, because the mountain is closer to the heating source, right? Closer to the sunshine. So what happens is that during the daytime, the temperature will rise up more significantly compared to the valley region, right? So because of that, there will be an air motion going upward over the top of the mountain, while the air will go downward over the valley region, and this is going to cause a recirculation like this, right? It's going to form this clockwise recirculation. So this is during the daytime. While during the nighttime, basically the mountain top will be very cold, while the valley region will be warmer. So that is going to form a counterclockwise air motion, right? So this is during the nighttime. So you can see that for these wind patterns, they happen on a regional scale. So one thing that I forgot to mention is that because of this land-lake breeze or land-sea breeze, and we're also going to see some weather conditions that's quite special for certain locations. For example, here what I'm showing is actually a satellite image of the Azores Island. Azores Island. Okay, so this is a series of islands that's in the Atlantic Ocean. It's a very beautiful place. So if you happen to have time or wanted to travel around over the world, you can feel free to go there, because that's a a very beautiful place, very beautiful islands. So so this is the satellite image showing the Azores Islands. So you can see that over the island there are a lot of clouds, right? So we call this effect as the island effect. And this is also because of this land-sea breeze. So what you can see is that basically over the during the daytime, so what happens is the water or the wind is blowing from the sea over the land, right? So what that means is that basically the air with a higher relative humidity will be introduced over the land, right? And further, this air with higher relative humidity will rise up, and then we know that the temperature will cool down, right? Because the higher you go, the lower the temperature. And because we have such a large amount of water vapor, we're going to form clouds over the land. And this is also called the island effect. You can see that this is because of this land-sea breeze influence. So this is the wind pattern over the regional scale. So what about the global scale? So here I have a short video that's showing the transport of aerosols or particulate matter over the global scale. So let's see this short video here. So basically you can try to find what is the basically you can try to find what is a general pattern in this transport of the aerosols. So let's see if it works. Okay. So you can find out that basically near the equator, you can see there's a lot of particles being transported. Actually, they're being transported from the east to the west, right? If you watch the general pattern, that's traveling from right to left, which is east to west. So you can also see that there's wind, let's say over the United States, which is on the top left corner here. So you can see that in general, the wind pattern is from west to east, right? And further at higher altitudes, you can see that, for example, over the Canada, right? Further in the Arctic Circle there. So you can see that wind pattern is actually reversed. It's from east to west again, okay? So similarly, you can see there's a symmetry over the southern hemisphere. Okay, and also you can observe there's a lot of swirls or tornadoes, hurricanes, whatever you want to call them, or cyclones. Right? So different color here represents different types of particulate matter. For example, the dust are shown in these red colors, right? The green color represents organic and black carbon, right? So these particles are generated during the wildfires over the forest. Sulfate, basically it means the sulfur dioxide. They're reacting with other species in the atmosphere, and they can form the particulate matter. So typically the sulfates represents industrial level. So that's why you can see there are quite high concentration over the United States, pretty high concentration over the Europe, pretty high concentration in India, right? And very high concentration over China because of the pollution over there. So there are also there's also blue color of the aerosols that represents the sea salt, which is coming from the waves over the ocean, while they basically the wave hitting each other, right? Generate those tiny particles. Okay, so you can see that from this video here, there is general patterns in terms of the pollutant transport, right? For example, over the United States, you can see that actually most of the particles are directly transported from west to east, right? So let's say if we ask a question, where should we where should we set up our coal-fired power plants or the polluted industry, right? So we would prefer to set it up over the east coast because the wind is directly blowing these pollutants over the ocean, and probably also blowing them over the Europe, right? But at least it's not harming the citizens in the United States. And also these pollutants can be mitigated over the ocean, right? But if we set it up on the west coast, then these pollutants will just flow over the United States and maybe cause some problems. So this is talking about the wind over the global global scale. So what is happening there? Okay, So let's come back to our slides here, right? So it is also asking question, what are the features of the wind? And are there some general features? And we went through that. So basically, this wind here is also because of the temperature difference. So you may wonder why there's temperature difference, right? So this temperature difference is just because our Earth is not flat. Our Earth is a sphere, right? By having the Earth as a sphere, then we know that for each, so basically this is dividing our Earth into different regions, right? So let's say if we look horizontally, the distance, and in each band here, they have the same distance, or they have the, let's say, the same height here, right? We know that the solar radiation basically comes directly in this way. So theoretically, the radiation in each band here should be the same, right? Their radiation is the same. But if you notice that on the Earth, basically for each of this vertical band, they cover a different region or different area of the Earth, right? For example, over the Arctic region, we're covering a longer distance. So what this means is that the solar radiation over the Arctic region will be lower, right? The radiation or the heat that's directly coming from the sun is going to be lower. Well, during the or over the equator region, the solar radiation will be stronger, right? So what this means is that the temperature here will be cooler and temperature here will be hotter or warmer, okay? So based on our definition of the air movement, we know that air will settle down, right, over the Arctic region, while the air will rise up over the equator region. And by having this movement, we know that air should be going this way. Okay, so this is indeed the case, but this only happens if our Earth is just a ping pong ball, or if it's a billiard ball, very small sphere there. But that's because the Earth is so large in its scale, so the air will not be very stable if it keeps traveling this way. So what happens is that this large circulation is broken up into 3 different circulations, right? So first circulation is happening near the higher altitudes, okay? So what happens is that the air will move this way, right? This is the first circle. And then we're going to have the second circle that's going this way. And then we're going to have the third circle going this way. So you can see that the air is still settling down over the Arctic region and rising up over the equator region, but except that right now we have 3 different circulations, or 3 different cells, okay? So that's why we can break up this air recirculation into different cells, right? So as I have introduced, over the equator region, there's a circulation that comes in this way. So the air is warmer at the equator region, so it rise up, right? And then settle down over the mid-latitude. So we call this cell as the Hadley cell, okay? And in the mid-latitudes, this cell is called the Ferrel cell. And then we have this polar cell. So due to the symmetry, right, in the southern hemisphere, we also have these 3 different cells here. Okay, you can see that indeed it is because of the temperature difference on the Earth that's causing this global scale of the wind. But because the scale of the Earth is so large, so the wind pattern is broken up into 3 different cells. And but this is just talking about the wind directions on the northeast level, right? Up and down and northeast. But what is causing this wind from left to right or east to west? Okay, so you can indeed see that over the United States, the air is blowing from west to east. So that's why if you want to set up coal-fired power plants or the industrial pollutants, polluting industries, you should set it up over the eastern coast, right? East coast. So what is causing this wind to be blown from east to west? So the reason behind that is actually the Coriolis Force. So I'm pretty sure that you have gone through this contents during your high school, right? So here I will just briefly introduce that again. Okay, so the Coriolis force is just because of the air movement or anything's movement on a rotating sphere. So let's say now we're trying to look at our Earth from the North Pole. So what happens is that let's say this is our eye. Okay, this is our eye, and we're trying to look it from this way. Okay. So this is, we're looking at the North Pole. So let's say the air is trying to travel directly towards south to Chile, okay, Quito, Chile, okay. So what happens is that the air will originally go from the north to the south, but because of the Earth is rotating, because the Earth is rotating, so basically there's going to be a line speed, right? So the Earth is going to have a speed from west to east as the air is traveling from north to south. So because of that, the original air, since it doesn't have any velocity from east to west, so what happens is that it's going to deviate its trajectory, right? Further and further, and finally when the air reaches to the equator, the Earth has already rotated for some distances. Okay, so you can see that basically because of that, the air that's trying to travel from north to south will deviate towards its right. Okay, so the same thing happens if the air, let's say the air is trying to travel from south to north. Let's say the air is trying to travel to the North Pole from Quito, right? And then as it travels upward, because the air at the equator has a very large line speed from east to west. So what happens is that this line speed will be larger than the surface or the line speed at mid-latitudes, right? So let's say originally here the line speed is this large, but at mid-latitude the line speed of the surface is only this large. So what happens is the air will just go towards this way. Okay, so you can see that the air will also deviate towards to its right. So there's a easier way to memorize the direction of this Coriolis force or direction of this trajectory. So the way I memorize this is by saying because we're living on the northern hemisphere, so we're always right. Okay, so we're always going to turn right. All right, you can see that from North Pole traveling to the equator, we're turning right. And also from the equator traveling to North Pole, we're also turning right. Okay, so now let's look at what's happening over the Earth here. We know that the air is going to travel from from north to south over the mid-latitude, right? Because we're talking about the northern hemisphere, so we're right. So we're going to turn right here. Okay, so this is also giving the general direction of this particles near the equator that's traveling from east to west. Okay, and over the United States, we know that the air is traveling from south to north, right? If it's traveling from south to north, it's going to turn right, and that's going to give us this wind direction from west to east direction. Okay, so the same happens for the southern hemisphere. So the air traveling from south to north, right, it's going to turn left because northern hemisphere turn right, southern hemisphere turn left. Okay, so the same applies in other regions here. So this is giving us the wind direction from east to west in terms of this global scale here. So the same thing will apply for the cyclones or tornadoes, whatever you call them, or hurricanes. So typically, whenever we see these hurricanes, they're going to follow some patterns here. So it's going to have this like circular shape here, right? And actually, based on this circle here, we can tell which hemisphere it is. So whenever we see these hurricanes, what happens is that it has a low pressure center. Okay, so while the pressure surrounding it is higher, right? And then we know that originally the air is going to travel from outside inward, right, towards the low pressure center. So if we're at the northern hemisphere, what happens is that since we're going to turn right, we're going to go this way, okay? And also here it's going to this way, and here finally going this way. And because of that, finally the shape of this hurricane is going to look like this, okay? And in terms of the southern hemisphere, we're going to turn left, okay? So that's why it's going to have direction that looks like this, okay? So finally it's going to revolve basically clockwise. So northern hemisphere is counterclockwise, southern hemisphere is clockwise. But basically the underlying principle is still the Coriolis force is going to bend the flow direction towards its right, okay? So that's all for the, so we're getting to the end of the wind direction here. So finally, this global pattern here is also going to affect our daily travels. So for example, of course, right now, very few people will still take these flights here. But for example, if you're traveling from St. Louis to Seattle, we know that typically these flights are pretty long, right? So basically, if you're trying to fly from St. Louis to Seattle, you can see that the time is typically around 4 hours and 30 minutes. While if you travel back, it's just 3 hours and 45 minutes. So what is happening? Is it because the aircraft you're taking is different? Or is it because the pilot intentionally did that, right? They burn less fuel when they're trying to fly towards Seattle? It is not, right? It is because of the wind direction. Basically, the wind is pushing this aircraft to travel from east to west, right? So it's from west to east, right? So the plane is going to be easier if it traveled this way instead of this way. Okay, so that's why when you're traveling back, the time you need is actually shorter. Okay, so this is how you can see that the global wind pattern is actually affecting a lot of our daily life events there. So this is talking about the wind. The wind is, of course, going to affect the air pollutant transport. And we see that for both the regional scale and the global scale, the wind are able to pose some influence on the air pollutant transport. So now if we look at the condition that where there isn't wind transport, okay, so this is further looking at the vertical development of all of these pollutants. So this is more related to the design of the air pollutant generating devices. For example, the coal-fired power plants, we know that there are a lot of stacks. So how high should be these stacks, right? There are a lot of discussions on is it useful if we build a very high stack, right? If it's like 1 kilometer, 2 kilometers high, is it really useful in controlling the air pollutants? So based on the contents that I'm going to introduce further, you can see that they are going to pose some influence. Okay. So here, before introducing new contents, we have to understand how the temperature distributes vertically in our atmosphere. Okay. So so basically, for these two graphs here, what I'm showing is the vertical profile of the pressure, atmospheric pressure, and atmospheric temperature there. Okay, so in terms of the pressure, we know that the higher the altitude, the lower the pressure. That is for sure without any problem, because if you go really high there, that's just vacuum which is in the universe, right? But in terms of the temperature, it is actually quite interesting. So let's say if you go hiking in a mountain, right? So how does the temperature increase? How does the temperature change as you go further higher up? We know that the temperature is going to reduce, right? And this is actually because the air that's over the land surface, right? Let's say we're imagining a parcel of the air. As it travels up, because the pressure is so low, the volume is going to expand. And while the volume expands, so basically the air does work to the outside, right? We know that if it does work to the outside, the internal energy will decrease, so the temperature will decrease. Okay, so you can see that in the troposphere, which is the definition that I introduced during the ozone control, during the ozone hole there, right? So we know that in the let's say, in the troposphere, there's a high concentration of ozone, which is because of human activity. But in the stratosphere, there's an ozone hole that's happening because of the CFC introduction, or the release of the CFC from the Earth. So what you can see is that in the troposphere, which is typically around, let's say, 16 kilometers over the Earth, right? 16 kilometers, of course, it's going to include all of the human activities over the Earth. So you can see that the temperature is decreased. It's indeed decreasing, and this is because of the mechanism that I introduced. So the air rise up, it's going to do work to the outside, so the temperature is going to decrease. Okay, so why does the temperature increase in the stratosphere? And that is because of the ozone, right? So the ozone will react with the ultraviolet radiation and actually converts that energy into heat, while the ozone is not changed at all. Okay, so this is giving us more heat in the stratosphere, and further higher up, that's the mesosphere, and we don't care about that layer anymore. But the most important layer that's affecting our daily life is the troposphere, and we know that the troposphere, in general, the temperature will decrease as we go further higher up. So how much does it decrease, right? So people define this dry adiabatic lapse rate. So basically by using the air property over the inside the troposphere. So in general, for every 100 meter that we climb up, the temperature will reduce by 1 Celsius. Okay, so for example, if we go up a mountain that is 1 kilometer high, so the temperature will typically reduce 10 Celsius. So if you decide to climb up the Mount Everest, okay, so that's gonna be negative 80 Celsius, right? But since the ambient temperature over the Earth, let's say, is 20 Celsius, so the temperature there will be around negative 60 Celsius. Okay, so this is how the temperature changes as a function of altitude. But we have to know that this dry adiabatic lapse rate, people typically also use the gamma to represent that. So this dry adiabatic lapse rate is just in general applies for the atmosphere, but things can be different for different locations. For example, let's say we have a strong heating source that's over the land. For example, we're talking about the location that's near a coal-fired power plant. So we know that coal-fired power plant generally has more heat, right? So the temperature will be higher. So what happens there is maybe the temperature will be somewhere here at the surface, while the temperature profile might look like this. Okay, so they can be different profiles, but what we are showing here is how the temperature decrease in general according to the air properties. Okay, so this involves different types of air stabilities. So for example, here again I'm showing the dry adiabatic lapse rate. Okay, so this is showing that for different heights, right? If we rise from 200 meters to 400 meters, we know the temperature is going to reduce by 2 Celsius, let's say from 22 to 20. Okay, so now this dry adiabatic lapse rate is shown in these dashed lines in these two different scenarios. For example, we're encountering a situation where the surface temperature over the land is higher. For example, we're talking about the coal-fired power plant, right? It's releasing more heat, but it has a lower temperature at higher altitude. So what can this situation be? So it can be that some colder air actually travels towards our region, right? So we know that the air there can be cold or warm, and at different altitude or at different heights, there can be different parcels of the air. So for example, the air over this location becomes cooler, right? So then we're going to have this this type of temperature profile, and we call this lapse rate as the ambient lapse rate, which is the actual temperature profile there. So what's going to happen to the air motion under this situation? Okay, so let's again draw this air motion here. So we know that for this under this dry adiabatic lapse rate, what happens is that the air parcel will rise up, right, while it expands, right? So the temperature will decrease. Okay, so let's say under this situation, let's assume that the air also tries to rise up. Okay, so let's say it rises up for 100 meters. So it's going to follow the dry adiabatic lapse rate, because the temperature profile decides that, or the air property decides that it has to reduce this amount of temperature as it rises up. Okay, so for example, it rises up for 100 meters and got to this point. Okay, so now let's evaluate the air temperature for this location and also the surrounding surrounding location. So you can see that actually the temperature here is higher than the temperature that's surrounding this air parcel, right? So what that means is that we are having a warmer air that's inside this larger space here. So what happens is this warmer air will keep rising up, okay? So this air will just keep rising up higher and higher because of this type of ambient lapse rate here. So we call this type of air atmospheric structure as the unstable condition. Okay, so basically the temperature at the surface is too high here, while the temperature at higher altitude is too low. And then this will cause the air temperature to be always warmer compared to its surrounding temperature there. So the air will just keep rising up and rising up. And this is going to be excellent condition for the pollutant transport, right? So we want the air pollutant to transport to outer space and getting diluted, right? So basically, we don't want these air pollutant to get trapped under inside certain location there, inside certain space there. So that is the condition that's corresponding to this third condition here. So again, I'm showing the dry adiabatic lapse rate by this dashed line here, while the actual situation might look like this. Okay, might look like this solid line here. So you may wonder what is the condition that's corresponding to this. So you can see that actually this corresponds to the situation where the temperature of the surface is lower compared to the normal condition, right? So what can this situation be? So it can be during nighttime. So we know that during the nighttime there's no radiation. The land release heat or dissipate heat pretty fast, right? So that's going to give us a lower temperature. But at higher altitude or higher heights, it's not releasing the heat as that fast, right? So we may have this situation that looks like this. Or also at higher altitude, we might have a higher temperature or warmer air that's coming by, okay? So we may have this situation. Now let's see what's going to happen. So let's say that the air at the surface of this actual ambient condition also tries to rise up. So after it rises up for 100 meters, according to this dry adiabatic lapse rate. So if we compare the temperature of this air parcel towards or against the surrounding air, so you can see that the air temperature of this air parcel is actually lower compared to the environment temperature, right? So if the temperature of this air parcel is lower, then that means it's going to have a higher density. So the only way it can move is to drop down. Okay, so there's no way that the air parcel can rise up. Okay, although it tries to rise up, but because the temperature is too low, it's going to drop down. Okay, so under this situation, we'll call that as a stable condition. So you can see that the stable condition is very inefficient for the transport of the air pollutant, right? If we have a stack, right, let's say setting up at this altitude here, then there's no way that the pollutant will get transported to the higher altitude, higher space. So all the pollutant will just get trapped over this layer here, and there's no way we can dissipate all of these pollutants. So that is going to be bad for the transport of the air pollutants. Okay, so this is indeed happening in our daily life. So here what I'm showing is the picture of the San Francisco Bay. Okay, so this is picture is taken during the early morning. So we know that during the early morning, the temperature at the ground is actually very low, right? While the temperature at higher altitude is higher, which is because the radiation warm up the air here. So we're going to creating a perfect situation for the stable condition. And we'll also call this condition as the inversion, okay? So the atmospheric inversion. So you can see that a lot of pollutants are actually trapped very close to the surface of the land there. So it's not reaching to this, let's say, 16 kilometers. So a lot of the air transport is, a lot of the pollutants are just trapped at very low surface, at very low altitude over the surface, okay? So here I'm also showing another picture of the coal-fired power plant, and this is a picture in your textbook. So basically you can see that the stack cannot efficiently travel or efficiently release all of these air pollutants. So all of them are just trapped near to the ground, okay? So this would involve the design of the stacks. Okay, so typically what we want is that if people ask, is it the higher the stack, the better? It is, right? If we can build a stack that is higher than the inversion, then we can for sure make sure that all of these pollutants will not be released in our surrounding area, right? The higher the stack, indeed, is better. But we cannot build an infinitely high stack because there's a lot of cost associated with that. So then how can we predict the concentration of the air pollutants coming from a stack? Okay, so people have done a lot of study on calculating what is the dispersion. So basically this is the pollutant dispersion coming from a stack, okay? So people designed or come up with this model for the transport of the pollutant. Basically the air pollutants are being emitted from this cylinder here. Right, the cylinder can be assumed to be our stack. It has certain height, which is the h, right? And people define this effective height, which considers the vertical movement of the air initially when they're being emitted from the stack, because there is always a flow velocity of the air, right? So after this effective height, then we can think of the transport of the pollutant just along the direction of the wind, which is towards the x direction, okay? So if we put a monitoring site on the ground, which represents a z equal to 0, okay, so we can calculate what is the concentration of the air pollutant at any location. We can use this equation to do the calculation, okay, as long as we know what is the y location and what is the x location. So x location is just the location downwind of this the stack here. Okay, so there are some parameters involved. E here represents the emission rate of the pollutant. So there's Sy and Sz. These represents the plume standard deviations. The standard deviation just means how wide the spread, how the dissipation of the pollutant is happening. So for example, if we're talking about very slow speed of the wind, then it will actually help the dispersion of the pollutant to happen on the y direction and on the z direction. For example, here is dispersion along the z direction, while here is the dispersion along the y direction. And also, if there's no inversion, let's say the air is not stable, or it's under the unstable condition, then the dispersion will also become larger. Okay, so we can find out these standard deviation values based on the stability of the atmosphere. Okay. So also it involves the wind speed, right? And the XYZ just means the locations, okay? And since we know these parameters, we can just plot them in and calculate with these exponentials. So you can see that further, if you know the backgrounds of mathematics, these just represents the product of two Gaussian distributions. Okay, so basically this model just assumed that the dispersion along the z direction and the dispersion along the y direction are just the product of two Gaussian distributions. Okay, and so you can see that since we also involve the calculation of the effective height, we can also use this equation to calculate the effective height, which is the sum of the original height of the stack and then plus this delta h. So the delta h can be further calculated based on the velocity of the stack, velocity of the flow coming out of the stack, right? The stack diameter, the wind speed, right? The pressure, temperature of the stack, the flue gas, and also the air temperature. So after we plug in all of these parameters, we can calculate the delta H. After we have the delta H, we can plus that by the height of the actual stack to get this effective height, okay? So once we have this effective height and all of the other parameters, then we can calculate whatever concentration of the air pollutant at any location you want, okay? So since I mentioned, the standard deviation will depend on the atmospheric stability, right? So here are two figures showing how the standard deviation along the y direction and along the z direction is getting affected by the atmospheric stability and also the distance downwind of the stack. So basically this can be shown as x, okay? So x is the distance along downwind of the stack there. Okay, so you can see that indeed the dispersion is becoming larger as we further go downwind, right? So originally the dispersion is just like this wide, right? But further downwind, the dispersion will be very wide here, okay? Right? So they will increase as a function of the distance downwind, right? But also they depend on what is the atmospheric stability. So people will divide them into different stability conditions from A to F. Okay, so how does A to F depend on the stability? Okay, so here is a table showing how the stability is decided. For example, let's say we're under the nighttime. So typically the nighttime, as I mentioned, surface temperature is low, then it's more easy to have this stable condition, right? So the air is less efficient to be transported towards the outer space. So you can see that during the nighttime, actually, you have the conditions of D, E, and F, okay? D, E, and F. And actually, the less or the fewer the cloud, the more stable the condition is. So basically, this is also quite counterintuitive, right? So if you see, if you have a clear night, actually that's more inefficient for the pollutant to be transported away. That's mainly because if you have clouds over the nighttime, then that means the surface temperature at the ground will be higher. But if you don't have any cloud, then the temperature at the surface will be lower. And then that's going to be easier to have this type of condition, right? The ground temperature is actually lower compared to the normal condition there. So basically, if you have a condition that has fewer cloud coverage, then you will have a very unstable condition, which is corresponding to F. And you can see that F has the smallest standard deviation, okay? So by having the smallest standard deviation, then basically that means the spread of this plume is very limited, okay? So the spread of this plume is very limited, okay? But during the daytime, when there's very weak surface wind, okay, so that means the pollutant can get more easily dissipated, and then that's going to correspond to the A condition, where the standard deviation of the plume will be larger, okay? So you may see that let's say if we want to calculate the pollutant concentration at any location. So first we need to know what is the stability condition, what is the atmospheric stability, right? So one thing is that we have to refer to this table, right? Let's say if we decide that the stability is actually corresponding to the C condition. So basically, we'll first know whether that's daytime or nighttime. Then we'll try to know what is the solar radiation condition, right? Or what is the cloud coverage condition. And then we'll refer to the surface wind condition to find out what is the stability condition. And one thing we need to notice that under the overcast condition, basically that means the cloud is covering the entire sky. Then that means the stability condition of D, okay? So then we can, after we know what is this condition here, we can go to this table to find out what is the value. Let's say if we have the C value, and then we're talking about the measurement at 4 kilometers downwind the stack, then we can know that the standard deviation on the y-axis is somewhere between 300 and 400. While here, we can again trace this value here, right? You can see that the standard deviation along the z-axis is somewhere around 200 meters. So you may say that by referring to this table here, it's not very accurate. So what you can also do is you can use this table here to actually calculate what is the stability, what is the SY and SD. Okay, so people design these equations, and then you just need to plug in what is the X, which is the distance downwind the emission stack, right? And you can plug in these different parameters. Let's say for each stability condition, let's say for the condition of C again, okay? So if we're talking about the condition at 4 kilometers, then we're going to use the values of C, D, F in here, and then we're going to use the A value in here. Okay, so basically you can plug in A with 104 and then X with 3 kilometers and then calculate what is the SY, and then by using CDF, plugging them in here, X having the value of 3 kilometers, and then calculate what is the dispersion or standard deviation in Z direction. And then since we have all of these parameters, we can plug them in to calculate the concentration. So here we have an example problem from the textbook. Originally, I have a few slides to talk about the detailed method we use to solve this problem. So maybe you can go through these contents and then do some practice here. So basically, this is using the detailed process that's shown on this on the textbook. And then this is also one of the homework problem you are going to deal with for this time, okay? So although there are quite many calculation processes, but this is just plugging in the numbers we have in the textbook. So feel free to let me know if you have any questions. So finally, you may have the question, so what happens if our stack is within the inversion? Let's say we show those pictures, right? During night, we have that inversion problem, right? So what happens if we build a stack that all of these pollutants got trapped in the inversion? So how does that affect the pollution problem? So under that situation, we can basically calculate at what distance the plume reaches to the inversion top layer, okay? So that can be calculated by first find out what is the standard deviation on the Z location. So this is talking about the dispersion in the Z direction, right? So that is calculated by 0.47 multiplied by the height of the inversion layer, right? And then minus the height of the effective stack height. Okay, so by plugging in these values, we can calculate what is the standard deviation in Z direction, and then by using the C, D, and F, we can calculate what is the X location where the plume reaches to the top of the inversion layer. And then we can come up with further strategies to basically calculate how the concentration will look like under these situations. Okay, so you also have a homework problem on this aspect. So finally, let's do a review of our class this time. So basically, we introduced what are the major factor influencing the transport of air pollutant. That is the wind, right? The wind can be both in the regional scale and also the global scale. And later, we basically introduced how do we calculate this air pollutant concentration at the ground level. So we can use this equation, right? Once we have all of the parameters, okay? So we just plug in all of these corresponding parameters and then find out what is the concentration at any specific location. Okay, so feel free to let me know if you have any questions, and that's all for the contents of this class. Thank you.